So friends, this is a new numerical problem based on the shear force and the bending moment diagram. You can see that this is a uniformly varying load and this is the point load acting at the point E, and this is 1 meter distance. Okay, this is 1 meter and this is also 1 meter. This is the point distance between point C and D is 3 meter, and the distance between point A and C is 1 meter, and we have to draw the shear force and the bending moment diagram for this beam. Okay friends, so the first step is always to consider the reactions at the point A and B. So let us assume that reaction at A is acting in vertically upward direction denoted by RA, and reaction at the point B is also acting in vertically upward direction and denoted by RB. Now we know that friends, only vertical loads are acting over this beam. So reaction at A plus reaction at B will be equal to the net vertical load acting over this beam in downward direction. So in downward direction, this load is acting and this load is acting because of this UVL. So because of this load, there will be a load of 14 kilonewton acting in vertically downward direction, and because of this UVL, there will be a load of magnitude, the area of this triangle. So area of this triangle is half base is 3 meter into altitude, which is 20. So it will give us 44 kilonewton. Now friends, we know that summation of moment about the point A can be taken to be 0 because point A is a hinge. Now because of this RV, there will be a moment of magnitude RV into this distance of RV from the point A, which is equal to 1 plus 3 plus 1 plus 1 is equal to 6, and it will try to rotate the beam in anti-clockwise direction about the point A. Now because of this load of 14 kilonewton, there will be a moment of magnitude 14 into the distance of this load from the point A, which is equal to 1 plus 3 plus 1 is equal to 5, and it will try to rotate this beam element AE in clockwise direction. That's why taken as negative. Now because of this UVL, there will be a moment of magnitude which can be found out by considering the magnitude of this UVL acting at the centroid of the triangle. So suppose the centroid of the triangle is lying somewhere here. We know that the centroid of the triangles lie at a distance of 3 by 3 from this point D, and 2 by 3 into 3 from this point, that is from the point C it will lie at a distance of 2 meter, and from the point D it will lie at a distance of 1 meter. Okay, so this load W because of this UVL will be equal to how much? The area of this triangle, and the area of this triangle we have already calculated as 1 half base into altitude. Half base is 3 into altitude will give us 30 kilonewton. So because of this 30 kilonewton load, there will be a movement about the point A going in a clockwise direction. So clockwise is treated as negative and have a magnitude of 30 into this distance. 2 plus 1 is equal to 3. And it will give us the value of RV. When you put equal to 0, the value of RV will come out to be how much? 26.66 kilonewton, and the value of RA will come out to be 17.34 kilonewton. By putting the value of RV in this equation, you can find out the value of RA as this much. Now friends, we will find out the shear force at the point A, C, D and B. We have to find out the shear force. We will calculate the shear force at the point A on the left side of the point A and on the right side of the point A, denoted by this term, because there is a point load is acting at the point A. Similar is true for the point E and B, because there is a point load acting at the point E. That's why we have to calculate the shear force on the left side and on the right side. And for the point B, because there is a reaction acting at the point B, that's why we have to calculate the shear force on the left side of the point B and on the right side of the point B. Because shear force will change suddenly when going on the left side of the point to the right side of the point when a point load is acting at that point. And there is no point load acting at the point C and D, that's why we have to calculate directly shear force at the point C and D. So shear force at the point on the left side of the point A is 0 because there is nothing lying on the left side of the point A. Shear force on the right side of the point A can be find out by constructing a section on the right side of the point A. Suppose this is a section XX constructed on the right side of the point A. Now looking on the left side of this section, you can see that only this force is contributing toward the shear force about this section XX, and the magnitude of this force RA is how much? 17.34. So it will create a positive shear force of magnitude 17.34 using this sign convention. Why? Because if this is a section XX and this force is lying on the left side of this section and going in vertically upward direction, it will be treated as positive. Similar is the our sign convention, because if this is a section XX and if there is a force acting vertically upward direction on the left hand side of this section, it is treated as positive. Now shear force at the point C we have to calculate. Now shear force at the point C can be calculated by constructing a section here passing through the point C. Now looking on the left side of this section, you can see that this force Ra contributing toward a shear force of plus 17.34 kilonewton using this sign convention. Now shear force at the point D can be found out by constructing a section here passing through this point D. Suppose this is the section constructed passing through the point D. Now looking on the left side of this section, you can see that this force is contributing toward a positive shear force of magnitude 7.34 kilonewton, and because of this UVL there will be a force of magnitude 30 kilonewton acting at the centroid of this UVL of this triangle, and it will create a negative shear force of magnitude 30 kilonewton using this sign convention. Now because the shear force on the left side of the point E can be found out by constructing a section on the left side of the point E here. Now shear force on the left side of the point B will be same as shear force at the point D as we have calculated earlier, because the same calculation will repeat itself. So the calculation will repeat itself and will give us 17.34 minus 30. When you solve both of these, you will get minus 12.66. Okay. Now shear force on the right side of the point E can be found out by constructing a section on the right side of the point E. Suppose I am constructing a section here on the right side of the point E. Now I will look in the right side of this section. Okay, so on the right side of the section you can also look to find out the shear force. So looking on the right side of the section, only this force RB is contributing toward a negative shear force using this sign convention of magnitude RB, and magnitude of RB is 26.66 kilonewton, and shear force on the left side of the point B can be found out by constructing a section on the left side of the point B. So constructing a section here on the left side of the point B, this is the section XX constructed on the left side of the point B. Now looking on the right side of this section, this force RB is contributing toward a negative shear force of magnitude, how much? This is negative minus 26.66 kilonewton, because the value of RB is minus 26.66 kilonewton. It will contribute a negative shear force using this sign convention. Now shear force on the right side of the point B is 0 because there is nothing lying on the right side of the point B. Beam terminates on the right side of the point B. That's why shear force on the right side of the point B is considered as 0. Now we will calculate the bending moment, but before that we have to draw the shear force diagram. Now see this, on the left side of the point A shear force is 0, so making a cross here. On the right side of the point A it is going to 17.34. Suppose 17.34 is lying somewhere here. 17.34. Now on the shear force at the point C is 17.34. So making a cross here in the same level of 17.34 over the point C, and shear force at the point D is minus 12.66. So minus 12.66 suppose lies somewhere here. I am drawing with the red pen because it is making a little confusion. Minus 12.66. Okay, this was first. Now shear force on the left side of the point E is minus 12.66, will lie somewhere here. Shear force on the right side of the point E is minus 26.66. So suppose minus 26.66 will lie somewhere minus 26.66 up below the point E, and shear force on the left side of the point B is also minus 26.66, will lie in the same level of minus 26.66, and shear force at the point on the right side of the point B is 0, so making a cross here. So joining first point with the second point with a vertical line because there is a point load acting at the point A. Joining second point with the third point is a horizontal line because there is no loading acting between the point A and C. And joining the third point with the fourth point with a parabola. Now you can join these 2 points by this parabola or using this parabola because there is a UVL line between the point C and D. So both the parabola can be used. But which parabola to use? This is the question. So see here friend, we know that the loading of this UVL is increasing as we go from point C to D. That's why the shape of the parabola will be increasing parabola, because we know that the loading is equal to D, the slope of the shear force diagram give us the loading. So when the loading increases between the point C and D, then the slope of shear force diagram must also increase from C to D. So that's why we will take a parabola of this nature. Okay, so this parabola will be there. So you can see in this parabola, friends, if this is the distance dx, then this is the df, and if we go from the point C to D, if this is the distance dx, suppose, and this will be our df. So df by dx is increasing as we go from the point C to D, because loading value W is increasing for this UVL as we grow from point C to D. So this is the shape of this parabola. Now friends, from the point D to E, joining these 2 points with a straight line, these 2 points will be on a vertical line because there is a point load acting, and again with a straight line because there is no load acting between the point E and B. Join again these with to a vertical line, you can get your shear force diagram. Now friends, see this, we will find the point K at which the shear force is going to 0. Now at this point A, if we project this point K here, then we can see that it is meeting at this point. That is, here we have to draw a section XX in order to find out the distance of the point K from the point A, because at point A shear force is going to be 0, and we have to find out the value of the distance of the point K from the point A, okay, to find out the point where the shear force is going to be 0. Now for that, construct here a section passing through this point K. This is the section XX, constructed here at a distance of x meter from the point A, and this section XX is lying at a distance of x1 meter from the point C, suppose. Now friends, see this, we have to find out the shear force at the section XX and make that shear force equal to 0. Now how we will do that? Now shear force at this section XX, which is passing through this point K, where the shear force is going to be 0, is shear force at this section XX is equal to, because of this force, it will be 17.31 positive, and because of this triangle which is lying between the point C and this section XX, there will be a shear force which will be negative in nature using this sign convention, and the magnitude of that shear force because of this triangular portion of the UVL lying between the point C and the section XX is equal to half the base, which is x1, into altitude, which is Wx. Suppose where Wx is the intensity of the UDL at a distance of this x1, sorry, Wx1. This is Wx1, sorry. So where Wx1, I am writing it clearly, it is not visible. So this is Wx1. Okay. So this Wx1 is the intensity of this UVL at a distance of x1 from the point C. Okay. From the point C, this point K is lying at a distance of x1, and at that distance from the point C, the intensity of this UVL is Wx1, and at the distance of 3 meter from the point C, the intensity is 20 kilonewton meter. Now friends, we know that the shear force is given as the area of this triangle which is lying between the point C and the section XX as half base, which is x1, into altitude, which is Wx1. Okay, so this is the shear force. Now friends, we have to find out this Wx1. We know that, friend, at a distance of 3 meter from the point C, the intensity of the UVL is 20 kilonewton. Okay, so at a distance of x1 meter from the point C, from this point C, the intensity of UDL is Wx1. It is assumed here, Wx1. Okay, now we have to find out the value of this Wx1. So what we have to do? We have to divide these things, and we can find out the value of Wx1 as 20 into x1 divided by 3. Now you can substitute the value of Wx1 here, and you will find that Wx1 minus 1 by 2 x1 into 20 into x1 divided by 3, putting the value of Wx1 here. Now we know that shear force at this section XX is 0. So putting the value of shear force it is equal to 0, then you can find the value of X1 will come out to be 2.284. You can solve it by yourself, the value of X1, by putting the value of shear force at XX is equal to 0. Okay. Now we have determined the value of X1. Now the value of X then will be, the value of X will be equal to this distance 1 meter between point AC, because X is equal to how much? X is equal to AC plus CK. This AC plus CK. We know that AC is how much? 1 meter. Okay, from here. And the CK is how much? CK is X1. And the value of X1 is 2.814. So putting the value of here as 2.284 as the value of X1, you can find out the value of the X as 3.284. So at a distance of X is equal to 3.284, the value of shear force is becoming 0. Okay, at this distance 3.284 from the point A, the value of shear force has become 0 at the point K. Now we have to find out the bending moment at the various points. Now we will find out the value of the bending moment at the point A, C, D and B directly. We do not have to find out on the left side of the point A and on the right side of the point A. Similarly, we have to do it for the point C and D and B also, calculating on the left side and on the right side. Why? Because there is no concentrated movement acting at any of these points A, C, D and B. That's why we have to directly find out the bending moment at the point A, C, D and B. Now constructing a section here passing through the point A. Suppose this is the section XX constructed here passing through the point A. Now looking on the left side of this section, nothing lies. That's why bending moment at the point A is 0. Now constructing a section passing through the point C. Okay, and this is the section XX constructed here passing through the point C. Now looking on the left side of this section, this force is contributing toward a bending moment of magnitude 17.31 into this distance 1 of sagging in nature, which is sagging in nature using this sign convention. That's why taken as positive. Now bending moment at the point D can be find out in the similar fashion, okay, by constructing a section passing through the point D. Now I am looking on the right side of this section. Earlier I have looked on the left side of this section. Now I am looking on the right side of this section. So because of this force RB, there will be a bending moment about this section XX of magnitude 26.66 into the distance 1 plus 1 is equal to 2, and it will be sagging in nature by using this sign convention. Okay, so it will be treated as positive. And because of this force of minus 14 kilonewton, there will be a bending moment of minus 14 into this distance 1. Okay, and it will be hogging in nature by using this sign convention. So the bending moment at the point D will come out to be how much? 39.32 kilonewton meter. Now friends, we have achieved this bending moment. Now we will find out the bending moment at the point B, because at the point B, if you draw a section like this passing through the point B and look on the right side of this section, you can see that nothing is lying on the right side of this section XX. That's why bending moment at the point B is 0. Now we will draw the bending moment diagram. So, but before that we have to also find out the bending moment at the point K. So the bending moment at the point K, which is the maximum bending moment, which was at point K, which shear force is 0. So the bending moment at the point K, that is at X is equal to 3.284, we have to find out. We have constructed a section XX passing through the point K in earlier case, and its distance is X from this point A and distance of X1 from point C of the section XX constructed through passing through the point K. Now bending moment at the point K can be find out. Now look on the left side of this section. The bending moment because of this reaction RA will be equal to 17.31 into this distance X, and bend which will be positive in nature, that is sagging using this sign convention. And bending moment because of this portion of the UVA line between the point C and the section XX will be equal to how much? It will be equal to minus y, because it is creating a hogging bending moment using this sign convention, is equal to 1 by 2 half base, which is x1, into altitude is wx1. That is the area of this triangle. This triangle is half x1 into wx1, and it is acting at a distance of x1 by 3 from this section xx. That is at centroid of this triangle, this portion of the UVA triangle. It is x1 by 3, okay, from this section xx. So x1 by 3. When you substitute the value of x as this much, and x1 we have earlier calculated. You have to look, go back into the video where I have calculated the value of the x1. So we have already calculated the value of x1 as 2.284. So when you put the value of x1 here, and wx1 we have already calculated as 20, I have already shown you 20 into x1 divided by 20, x1 divided by 3. We have already calculated the value of wx1 also in the previous case. So if you substitute the value of wx1 here, and x1 can be put from here into this expression, and the value of x is substituted from here into this expression, then you can find out the value of maximum bending moment, which will come out to be 43.47. okay, so now we will draw the bending moment diagram. So draw a line like this that I am drawing. So this is the line drawn like this. This is the point A, suppose this is the point C, this is the point K, this is the point D, this is the point E, and this is the point B. Now bending moment at the point A is 0, so making a cross here. Bending moment at the point C is 17.31, so 17.31 will lie somewhere here. Bending moment at the point D is 39.32, so bending moment at the point D, this is 17.31, and bending moment at the point D is 39. So 39 suppose lies somewhere here, 39.32, and bending moment at the point B is 0, and we have forgot to calculate the bending moment at the point E also. So bending moment at the point E can also be calculated. I am here calculating because I have forgot earlier to calculate the value of the bending moment at the point E. It will be equal to sagging in nature because of this force RB is equal to 26.66 into 1 meter, and it will be positive in nature. So bending moment at the point E is 26. So 26 will lie somewhere here, suppose 26.66. And bending moment at the point B is 0. And bending moment at the point K, I have already calculated. The maximum is 43.47. So 43.47 will lie somewhere here, 43.47. So joining first point with the second, okay, with a straight inclined line, because between the point A and C, the shear force diagram is a horizontal line. So bending moment diagram will be an inclined line joining points, these 2 points, with a cubic curve, because the bending moment diagram is a parabolic curve between the points C and K, and you know that the shear force is decreasing between these 2 points C and K. That's why the slope of the bending moment diagram will decrease from point C to K. Okay, now joining the point, how it is decreasing, let us see. Why it is decreasing, let us see the reason. Because we know that shear force is equal to slope of bending moment diagram, which is equal to dm by dx. So because shear force is decreasing from when going from point C to K, that's why the bending moment slope diagram slope will also decrease as we go from point C to K. So it is a decreasing parabola. You can see the decreasing nature in this way. If this is dx, then this is dm, and if this is dx of the same length as dx drawn here, then this will be dm. Clearly the dm, the height of dm is decreasing here. It is having higher height, it is having lower height. So that's why it is a decreasing slope curve. And from point C to K, the shear force is increasing. So increasing slope parabola cubic curve is drawn from here, because shear force is increasing from point C to K in C to D in negative direction. That's why the slope of the parabola between the points C and D will be of increasing in nature. You can see this like I have done in the earlier case by drawing the dx element, and between the point D and E it will be an inclined line. Okay, and between the point B, E and B it will be an inclined line. So this is the bending moment diagram. So friends, I hope you like my video, and if you like my video, you can subscribe my channel and also press the bell icon for the notification of the upcoming videos.